And welcome back, AP Calc students. Time for more free response questions from old AP exams. Today we're going to be looking at the year 2019 and question number 2. So question number 2 is a calculator question, and it's also a blend question, which is the pattern that it seems that AP is starting to do in mixing styles, mixing topics within the same question. As you look at the question right now, you should immediately be thinking, well, it looks like it's a part table of values. That's true. It's also part PVA, and it's also got a little bit of a potpourri. There's quite a few things going on in this question. It's a very comprehensive. So let's first just look at and get a feel for what they want to know. This says the velocity of particle P moving along the x-axis is given by differentiable function v sub p, where v sub p of t is measured in meters per hour, and t is measured in hours. Selected values of v sub p of t are shown in the table above. Particle p is at the origin at time equals 0. Now, right away, a couple things. PVA, concept that comes up all the time. And remember, when we move this way, we're taking a derivative. We move this way, we're taking an integral. So you would probably anticipate, since they're giving us velocity or selected values, they're probably going to be asking something about acceleration or position. We're probably going to do some either Riemann sums or trapezoidal sum approximations. So that might be, you could anticipate that. We're graphing velocity, area under that curve will give us position. But the other thing that's a little bit unusual is it said it's a particle moving along the x-axis. And so it actually says at the beginning it starts here. And so we do have some negative values here, so it's definitely moving back and forth. Maybe it's a sinusoidal function of some sort. But the curve is, the particle's moving along the x-axis, so it's doing this. And so it wouldn't be surprising if they want to ask about total distance versus distance, because we do have some negative, so it means we're going leftward. But the other thing that's additionally unique about this question is, even though a particle is moving along the axis, they do decide to give it units for distance and time. And so this is meters, and the time unit is hours. So that's a little unusual. And so they're calling this point P. And so since they're calling this point P, they're telling us the velocity, so v sub p of t is equal to some function, and here's where they're just giving us selected values. And so if there's v sub p, there's a good chance there's going to be a v sub another value. And they oftentimes put p and q together. The thing that's just a little thing that could be a little confusing is you see v sub p and you're thinking, does this mean position or something? No, this is just the point p. They could have called it anything. But the particle starts with p, so that's oftentimes why they use p here. So this is what we have, a particle moving along the axis. There's some selected values, and now they're going to ask us some questions. And it is a calculator question, so we're going to be having to more than likely use our calculator to do some of the values, but even if it's a really good process to go through, even though you may not have this sophisticated a function or a type of problem to do. So normally I would just go ahead and plot this. And I think I will go ahead and do that. I'm just going to move this down. Let's go ahead and put these down here. So our time axis, horizontal axis, will just go from 0 to 4. And looks like vertically we'll go up to 55 down to negative 28. So if we're strategic here, I think we can fit this in with no problem here. Try to make this relatively uniform here. Let's go 1, 2, 3, and 4. So that'll give us 4 here. This is our time axis, and so our velocity here, we start at, we need a point here at 0, and point 3, I'm just going to put in here point 3, make it relatively close. 1.7 would be about right there, and 2.8 would be about right there, and then we have 4. So these other values that I put here, technically I was implying that to be 1. This is 2, and this point here was 3, and all the circled values are the tick marks. Okay, and then vertically, let's see, we just have these two values really, so I'll just put 55 right there, and then down a little lower was 48, and then looks like we had a value at, so we can go about here, negative 29. So at 0, 0, we have a value, and then at 0.3, we have a value all the way up here at 55. 1.7, we are down at negative 29. 2.8, we return to this height here at 55. And then at 4, we are at 48. So it's possible, based on the selected values, it's possible that we have this going on. Maybe. Because the selected values, there could be more oscillation going on, not sure. But it gives a little bit of a feel for what's going on. So time, velocity, all right? So let's go to part A and see what we can figure out. All right, part A says, justify why there must be at least one time in the interval from 0.3 to 2.8 such that the derivative of the velocity or the acceleration of particle p equals 0. Okay, if they give us an interval, right away you want to be thinking, is this an intermediate value theorem question or is this a mean value theorem question? Because they're giving me an interval and then I have to explain why it's going to equal a value in an interval, and you're like, okay, which one of these is it? So let's look at it a little closer, see if we can figure it out. Justify why there must be at least one time in the interval. In this x interval, there's going to be a time in which the derivative is equal to 0. Well, the fact that they say the derivative of velocity, that's making me think more mean value. Because remember, intermediate value theorem is really a pre-calculus rule. Just a very quick review here. Pre-calculus that says, well, in an interval, A to B, we are always trying to prove that a value exists between the y values. And it's usually it's if f of a is positive and f of b is negative, prove there's a 0 in the interval. Or they'll just give you a range here for your y values, and you have to get a value in the interval that's in the range here. Whereas mean value is all about slopes of secants versus tangents, average rate of change, instantaneous rate of change, and it's is the slope of your secant, is there a point that's going to be where the derivative is equal to the slope? Doing this very quickly here. So the fact that I'm seeing derivatives making me think mean value theorem. So if it's mean value theorem, then that means I'm going to be doing mean value theorem review, which says the mean value theorem says if you have an interval, that means that the slope of the secant, which is just a rock, algebra 1 slope, slope of the secant, all three of these things are the same here, okay? That where is there a time where the derivative of the function, there's a c value in the interval where this is true, and the c value is in the interval a to b. So I would say a less than b is less than, a is less than c is less than b. There's a c value in the interval where the I rock is equal to the a rock, or the slope of the tangent is equal to the slope of the secant. This is the mean value theorem. You can think of it any of these ways. And graphically, that picture I actually just erased, which we had, I gave you this function, and I said, is there a time where here's the slope of the secant, there's the tangent. They're parallel, they're the same. So that's what we're looking for. So in this particular question, what's a little bit unusual is it says, prove that it's equal to 0. So instead of, shouldn't have just erased that. Instead of having this picture where you can say, well, this is going to equal this, it's slightly different where they're saying, okay, well, it's going to be more of that picture where both the slopes equal 0. This is like the slopes both equal 1. So here's what we're going to look at. We have the interval and we can just check it. So here's what we have. Let's do, I guess this is velocity. Let's figure out what is the velocity, and I'll put sub p since it's the point p. What is the velocity at 2.8? And the at 2.8 minus the velocity of point p at 0.3 over 0.3. Looks a little disproportionate there. Okay, let's see what the slope, the average rate of change is, or the slope of the secant. Well, the velocity, according to the table here, at 2.8, 2.8 it's 55, and at 0.3 it's 55. Oh, well, now I see why they're saying 0. So 55 minus 55 all over, who cares what the denominator is, but I guess this is 2.5. We get 0 over 2.5, so it equals 0. So the slope of the secant is 0. Well, if the slope of the secant is 0, it's saying, justify why there must be at least one point where the derivative is equal to 0. Well, we just showed that the slope of the secant is equal to 0, so of course the derivative would then have to equal 0. So now that we have shown that this is equal to 0, then we could say, by the mean value theorem, there exists a value C in the interval, and we're going to say 0.3 is less than C is less than 2.8, such that the derivative at C, which is actually equal to the acceleration, by the way, at C, it's equal to 0. Because that is what the mean value theorem says, that there does exist a point in the interval, if the function's continuous and differentiable, that the mean value theorem says that this is true over here. So the fact that we got 0, and they asked us to prove that the derivative equals 0, we first had to justify the slope of the secant was 0. So if the slope of the secant is 0, the mean value theorem says, well then yes, there's a point in the interval that the derivative will be 0 as well. So all you had to do was actually do the AROC and show that it was 0. Okay, so that is A. Not a very difficult question, but just understanding the lingo. Let's look at part B. Part B says, use a trapezoidal sum with 3 subintervals to approximate the value of this integral. So we're integrating from 0 to 2.8 the velocity function. So remember, the integral of velocity is equal to position. I'm actually going to put that up right here. Okay, so we're actually estimating the change in position here from 0 to 2.8. So this one's a little bit weird. It's always frustrating when one of them's negative, and the picture looks really funky, so you just want to trust your rule with the trapezoidal rule. And we're not doing the entire interval either, so you got to be careful there. It says use it from 0 to 0.3, and then 0.3 to 1.7, and 1.7 to 2.8. So we don't use this last interval. So the picture might be a little poor here. So I'm going to have, there's one edge of my trapezoid, and it doesn't even make a trapezoid here, it makes a triangle. But this is my first region right here. And then 0.3 to 1.7, well, that goes negative here. So that makes that actually is going to make 2 right triangles. So I don't even have a trapezoid yet. And again, this is weird. I'll lightly put that through there. Okay. So we're going to have part above, part below. We'll see which one wins that. And then at 2.8, we're at 55. Okay, so if you could imagine it, here's our first one. Maybe I'll switch this here. So we're going to be finding the area of this, and then we're going to be adding that to the area of whatever the difference is between this one, because part's above and part below. That would actually represent my second interval. And then the third one right here, we have 2 of these that are kind of hokey. Because of this negative here, it's giving us a very weird, it's not really giving us a trapezoid. It's giving us 2 triangles. So we have that. So graphically, it looks terrible, but just follow the rule with the rule for a trapezoid and we'll be fine. So remember, the trapezoidal rule, we have the average of the bases times the height. So if you remember, in geometry, whenever you have, you're trying to find the area of a trapezoid, we've got base 1 and base 2, and we need the height. Okay? But since we're doing this way, our bases are vertical. So it doesn't matter which one's which. There's base 1 and base 2, so we need to average those, and then the width of the interval will give us the height. Okay, so again, from geometry, b1 plus b2 over 2, there's the average, times whatever the height is. So we're going to use that formula here. Okay, so let's see what we can do with our first one. So our first one winds up being, so I'm just going to put in parentheses, here is our first trapezoid. It's going to be the height at 0, which is 0, plus the height at 0.3, which is 55, all divided by 2, so there's the average of the bases, times the height, which is the width of the interval, which is just 0.3. This is ugly. Okay? Trapezoid number 1. Trapezoid number 2. It's going to be the height at 0.3, which is 55, plus the height at 1.7, which is negative 29. Again, just trust the rule. Don't trust the picture is goofy. Divided by 2, and then we're going to multiply that by what is the width of that interval. And that interval width is going from 0.3 to 1.7. That's 1.4. And I'm going to take our little picture out of the way here to give us some room. Okay, so that's going to be times 1.4, trapezoid number 2. And for our third one, width at 1.7, or length there, negative 29 plus the width at 2.8, which is 55, divided by 2, times the width of my last interval. Well, 2.8 minus 1.7 is 1.1. That is ugly. And so from there, because this is a calculator question, I would completely go to the calculator for this one. And I wasn't going to do this before, but I decided to. I should have written this down first, but just so I don't lose anybody here. This was actually what I was doing here. I was using my velocity, and so I was saying, well, what is the... I'm not going to put subscript p because that'll be too cluttered here. So I was doing v of 0 plus the velocity at 0.3 divided by 2 times 0.3. That's how I got that first rectangle, or first trapezoid rather. Okay, plus the second one, I was doing the velocity at 0.3 plus the velocity at 1.7, all divided by 2, times the width of the interval, 1.7 minus 0.3, which is 1.4. Whoops, 1.4. That's where I got that. And then the last one was the velocity at velocity at 1.7 plus the velocity at 2.8 divided by 2 times the width of the last interval. 2.8 minus 1.7 is 1.1. That's where those values all came from. So then they were up there, and then it was time to just throw it in a calculator. So very tedious work here. Just for the sake of time. For the sake of time here, I'm just going to tell you, if you throw all of that in your calculator and do all of that, what you're going to get is 40.75. Okay, so again, trapezoidal approximation. And remember, what do you get when you integrate a rate or you integrate velocity? You get a change in position. So 40.75 is the trapezoidal sum here, but it's representing my change in position from 0 to 2.8 hours for this particular, for particle P. Okay? Let's move on to part C. So part C says a second particle, Q. So let's erase some work here. Make some space here. All right. A second particle, Q, moves along the x-axis for this 4-second window. And its velocity, now they give us that velocity. Okay, so I'm going to put, we'll put that here for now. And let's see. I'll put the C right here. We'll see if we have enough room here for everything. All right, so now they tell us that the velocity, and now it's a Q, so V of Q is equal to this function, 45 rad t times the cosine of 0.063 t squared. That's messy. Okay, so there's our velocity function. They love to throw those sinusoidals in there because they like when the particle goes back and forth. Okay, so that's in meters per hour. Find the time interval during which the velocity of the particle is at least 60 meters per hour. So the question is, when is the velocity at least 60 meters per hour? Well, what we're going to do here is we're going to graph this. And so what I want you to think about is I'm going to graph this function, see what it looks like, and then I'm going to graph 60 and see when it's at least 60. And so I'm going to do this in a process here. Stick with me here. This is see if you can follow this. So I'm going to go on here. I'm going to go into y equals here. Okay. And this little sequence of events is kind of important here. So it should be in radians. Okay. So I just want to graph the function and show you what's going on. So I got 45. Second function rad x. Obviously your calculator will turn all the t's into x's. Make sure you get out from under the radical. Cosine 0.063 x squared. Okay, so this is this kind of weird function. All right, and now I'm just going to graph it, but I'm not going to tweak the window at all, okay? And so you can see you don't get much here. It's kind of weird. And so the domain of the problem here, it says from 0 to 4. So all of this other stuff isn't very helpful. So the first thing I'm going to do is I'm going to say, well, I'm going to change this to my x minimum, which is my time, is to 0, and my maximum is going to be 4. And so if I decide to graph that update, there's 0 to 4 seconds. Not very helpful. You're like, what the heck is going on? Well, the problem, you can see that we just have a little thing right there. Well, the question said they want to know, when is the velocity at least 60? Well, remember, the horizontal axis is time. And in fact, let's go back to this graph right here. This is time. This is your velocity in meters per hour. So what they're saying is, when is this 60 or greater? So that was their question. When is the velocity of Q, of point Q, when is it greater than or equal to 60? That's what they want to know. Well, if that's what they want to know, yes, 60 is way up here off the calculator. Whoops, let's go back to my graph here. Because the calculator, we went from -10 to +10. So we're going to have to really adjust our y-axis so we can get up to 60. So I'm going to go back to my window and say, well, for my y-axis, I'm going to say, well, I don't really care about my y minimum. I'll just put it at 0. And for my my y maximum, I'm going to go up to 70, 75. Maybe that'll get it covered. Okay, and I'm going to graph that. Okay, so you can see that there's the zoomed in part of the cosine function we were looking for. And now here comes y equals 60. Oh, I was waiting for y equals 60, and it's not there because I didn't put it in there. So now let's see where y is equal to 60. That's just a horizontal line. Okay, and you can see that coming across. So you can see it intersects it at 2 places. So I just need what those 2 values are. So I go to my calculator and I say, where do those intersect? First curve, second curve, guess, and I get 1.866. So where does this happen? This happens at t is equal to 1.866. And for the sake of time, I'll give you that second one. You could see it intersects a second time over there, and that turned out to be 3.519. Calculator skills. Okay, so the graph, just to scoot this, I'll sneak that little graph in up here. The graph that went for this one, it looked something like this, where the function did that, and here was y equals 60 was right there. So these were the 2 values we were looking at, and that's where this was, I'm just going to put 1.8, and this one was at 3.5. Okay, so that's what they're saying. When is this above there? Okay, so we got those 2 values. So it says the second particle moves. Okay, find the time interval for which the velocity of the particle is at least 60. Well, it's going to be between here, so I guess the time interval is going to be 1.866 is less than or equal to the time is less than or equal to 3.519. Okay, and we got that by our calculator. Okay, Then the rest of the question says, find the distance traveled by the particle q during the interval when the velocity is that high. Now, here's what they're trying to get you with. Always, always, always. They're always going to be testing you on these PVA questions is what is the difference between integrating velocity versus integrating absolute value of velocity. And hopefully at this point you are automatically going, oh, that's going to be displacement. This is going to be total distance. This one over here, this is the rocket that goes up a mile and comes down. Goes up a mile high. And if this went up a mile, my displacement when it lands is 0. Total distance traveled, 2. So this question is saying find the distance traveled. It's not saying displacement. So it's going to be absolute value. So calculator time on this one as well. We're just going to integrate from our two values here. So I'm going to put 1.866 to 3.519, and we're going to integrate this velocity function v sub q of t dt. Okay, and that is all calculator work in there. Whoops, absolute value. Almost forgot the most important part there. The absolute value here. Okay, make sure it's really want to stress that here. Let's move this over. Absolute value of that to get your total distance. And again, for put that in your calculator. You know those buttons, you're going to get 109 approximately. And since this is the integral, this is position, this is going to be meters is what we are in. Okay, so that's how far it traveled going faster than 60 meters per hour. Okay, and I think we're good there. So now part D. See if we have enough room down here to do the rest. Part D says, at time t equals 0, particle q is at position -90. Use the result from part B and the function v sub q from part C to approximate the distance between the two particles at 2.8 seconds. Okay, I'm going to just draw a little sketch here, just so you get a feel for what's going on. So here's the deal. Remember the other point there? The particle started along, it's moving along the x-axis the whole time. Okay, it's doing this, da 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 da. And in fact, didn't we approximate from part B that the particle was, the position was 40.75? So whatever the position is, let's just say it's right here. Okay, at 40.75. There's particle P. The other particle is moving along somewhere, and it stops somewhere. I don't know, maybe it stops here. That's where particle Q stops at 2.8. So what they're saying is use this approximation, solve for this one, and tell us how far apart they are after 2.8 seconds. That's what they're saying. And again, you guys, the way I got this number, 4.75, is from part B. We found the position at 2.8 to be 40.75 rounding here. Okay, approximating. And also, our initial position was 0, and so we don't have to worry about adding that to it. But now we have to find out the position of Q at 2.8, and they give us a different initial position, and we'll have to solve that. So let's figure out what that is, and then we'll see how far apart it is. So what we're going to do is we can say, well, let's integrate from 0 to 2.8 of the velocity function for Q. So v sub q of t dt, that's what we're integrating, and it's going to produce position. Now for this one, just so we don't have a lot of confusion with values, remember we're doing sideways motion, so it's going to be x sub q. Well, that would equal x sub q of 2.8 minus x sub q of 0. All I'm doing is the fundamental theorem right there. Okay, so remember, position when you're moving sideways is x. So if you guys remember, they'll use the letter S for position, or they'll use the letter X. They'll never use a P. Okay? So what they're saying is they want this number. They said, where does the Q end at 2.8? So we're going to have to take the initial position of Q and add it over here. So I'm going to say, well, initial position of Q at 0.0 plus the integral from 0 to 2.8 of V of Q is going to give us where x of q was at 2.8. So it's a calculator question. Now remember, in the question it says, right away on part D, it says at t equals 0, particle Q is at position x is equal to 90. So we can just substitute that in right here, and we can say, well, that's going to be 90 plus, and then this is just calculator work. Okay, and if you put that in your calculator and integrate this, this is again by a calculator, you would get a 135.938 rounded. 0.938 rounded. Oh, this was a negative too, wasn't it there? Okay. All right, so if we add those together, you're going to get 45.938. Okay, so that is what the position of Q was. Well, now that you look at it, they're actually fairly close. Point Q was at 45, and if point P over here was at 40.75, so actually fairly close. So they said, how far apart are they? Well, we'll just subtract these. So the final part we would say is 45.938 minus 40.75, and we can throw that in our calculator. But I think we're going to get 5.187. 5.187 meters apart. Okay, that would be our final answer. So, this one's a pretty involved question, so to summarize this one from the top, a lot going on here. So the first one was a mean value theorem. Okay, you got to keep straight your mean value theorem versus your intermediate value theorem. Then the second question was just using a trapezoidal rule, and it was a little bit weird with the negative in there. The picture is not real pretty, but that's because you have a negative value. But just follow the rule. And then part C was now we actually had a function. We had to use our calculator and get the values and then integrate. The nice little part here, total distance traveled versus displacement. And then our last one was a fundamental theorem question with a second point, and it was just sort of weird. So this was kind of an involved one. A lot of details here, and so you want to look at it really carefully. Get that one. So there it is, 2019, question number 2, which is calculator 1. Thanks for watching. We'll see you next time.